Log on, tune in, find out. Another good idea from Cambridge.
Very delighted to welcome a very good friend of mine, Marco Di Francesco, the first Italian to teach me to proper pasta and so forth. For these seminars, where he's going to speak on the Hughes model of pedestrian flow in the one-dimensional case, because as far as I remember, it's pretty damn hard anyway. Please, Marco.
Thank you, Clemens. So thanks a lot for the invitation, and thanks also for the presentation. As a matter of fact, there's a big competition here in Cambridge about being the reference person for the pasta. You know, there are many Italians, so it's really a honor. Okay, so so my talk will be about the Hughes model for pedestrian flow. I will tell you in a minute what it's about. Let me mention that this is a working collaboration with the group of, so part of the group of Peter Markovic in Cambridge, in particular with him and with Jan Pichman and with Marie-Thérèse Wolfram, who is now in Vienna. So I'm going to start with introducing the model and also trying to show you that the model itself, as Clemens just said, is really hard to study, and so I'm going to try to modify it a little bit and try to make it less hard to produce a suitable mathematical theory. All right, so there are many attempts to model pedestrian flows, or in general human crowds. Some of them are microscopic, and for instance, the one is due to Helbing. Then there's also a way by cellular automata and models with collision avoidance. Then in the macroscopic case, there have been some gas dynamic type models, and also more recently mean field games type approach. Also Bertrand Maury and Filippo Sant'Ambrogio developed a nice model with say within the context of gradient flows, and there is also a literature related with conservation laws, which is actually more or less also our approach, and this is due to the group of Rinaldo Colombo and other people in Brescia. So our model was introduced by Roger Hughes, and it is actually a model which is, let's say, it's distinguished from other type of models, especially in those situations in which you have a very high density. So it's really suitable for crowded regions, for densely crowded populations. And in particular, there have been some, you can find in the literature also some examples in which this model has been applied with simulations, also in particular to the annual Museum Hagi, which is some very interesting application. Okay, so here is the model. It's a very simple conservation law, as you can see. So rho is the density, and here, the equation is coupled with this stationary equation for a potential phi. I'm going to tell you in a minute what the whole ingredients model in this equation. Let me just define all the objects. So x will be the position variable, and so it stays in RD in a more general framework. T is the time variable. Rho is the crowd density, as I said. This potential phi is somewhat denoting the common sense of the target for the people. So the people basically move according to the gradient of this potential, and I will settle the boundary condition for phi in such a way that this potential is basically the minimum at the boundary. So you have to see the boundary of the domain as the gate, so where people want to go somehow. So I have a maximal density, which is normalized to 1 for simplicity, and which is contained especially here in this term 1 minus rho here in the equation. Also here I'm going to explain in a minute what this means. And as I said, the boundary conditions are 0 for phi. I'm going to be more precise later on about the boundary condition for rho, so allow me to skip it for a moment. We have an initial condition for the density, of course, So now let me try to explain more or less the meaning of the model. So let me try to give a very naive derivation. You start with just a continuity equation. So you set somehow v to be the velocity of your pedestrians. Okay, now write p in a polar notation. So denote by z the unit vector, and then you have the modulus of v here. Now, first of all, I want to model the speed, so the absolute value, if you want, of my velocity to become, to behave linearly with the density and to be 0 when the maximum reaches the maximum, clearly. Now, what about z? So what about the direction of the velocity? I'm going to settle the direction to be parallel to the gradient of the potential, clearly. So that means that they aim to proceed towards the boundary, which is the gate, and the boundary is a place with 0 potential. So the potential is always higher than 0, right? And I want to direct towards the regions of least potential. So how do I do that? If you want to do it in a very naive way, you could just take phi to be the distance from the boundary, right? So it's something that you can do. So my measure of the boundary is just a distance. I just measure the distance from the boundary. In that case, I would obtain this very easy iconal equation for the potential phi with 0 boundary condition. Now, what we want to do here is a bit different. So we want to assume that the individuals temper their estimated travel towards the boundary by avoiding high densities. So they feel somewhat farther away from the boundary when the density is very close to 1, right? So if you want, you can see that in this way. So suppose this is your domain omega, right? If you don't temper, so if you take a classical iconal equation, I would have just a level set of my potential. So this one could be a level set for phi, right? If I now assume that I have some more crowded region here, for instance, then the level set would be rearranged in such a way that people would feel farther away from the boundary. So the level set of the potential phi are modified because of that. So the direction is changing. Okay? Okay, so what are the mathematical difficulties of this type of model? After all, you might say this is just a conservation law coupled with an iconal equation. Both type of models, let's say they feature a well-known and widely developed theory, right? But the problem is that they are coupled, and the coupling is not so nice. So first of all, of course, let's start with the easy things. Those we are sure to handle. How to handle? First of all, we have a nonlinear conservation law, right? And so we know that in certain cases you might have non-uniqueness of weak solutions. So you have to develop a theory which allows for discontinuity. In particular, in order to get uniqueness, you have to assume you have to define a notion of entropy solution, right? Second, the vector field grad phi, and here we come with the first difficulty. The vector field grad phi may be discontinuous on certain subsets of omega, because phi is just a solution of some kind of iconal equation with the inhomogeneous, let's say, right-hand side, or non-constant right-hand side. And as you can see from the equation, so let me go back for a moment to the equation. Yeah, you see, if grad phi is discontinuous here, I have some problems, right? This can be seen as a conservation law with a discontinuous flux. Where the discontinuity depends on x. But now the problem is, and here I come back to my difficulty, the discontinuity may be depend in time. Actually, in general, they depend on rho itself. So it's there is some kind of non-locality in this model. Because depending on how rho is distributed on my domain, that implies certain discontinuity of grad phi, and therefore I have some discontinuity appearing in my conservation law. All right? And then there's one last difficulty, which is this term 1 minus rho here. So let me go back. Yeah, this term 1 minus rho. So when rho approaches 1, then the gradient of phi goes to infinity. So this is one additional difficulty of the model. All right. So how to avoid that? Okay. So I hope I was able enough to convince you that the model is difficult. So now I want to I have to be as able in showing you that my approximation is acceptable. Let's say so. It's a feasible approximation. So first of all, a very naive, or if you want, very natural way to avoid discontinuity for grad phi is to add a little bit of viscosity in the Eichhorn equation. Right. This is very natural. What is the problem? The problem is that you still don't solve this problem here. So f of rho, I remind you, let's keep it in mind that f of rho is 1 minus rho. So I still have some possible unboundedness here, right? So another thing that you can do is to multiply. So before you add the viscosity, you multiply the equation by f squared of rho, and then you add the viscosity, right? That looks much nicer, because at least it seems you have avoided unboundedness of the right hand side. On the other hand, this left hand side here is certainly more difficult to study if compared to this one. So I would like to avoid this. I prefer this one. And so here we come to the end of the approximation procedure. What I'm going to do is the following. I prefer this left-hand side here, and I'm going to add one more approximation parameter, delta 2, to avoid this, let's say, degeneracy in the denominator of the right-hand side. All right, so I guess now I have to make a big effort in trying to convince you that this approximation is not so bad. Okay, this is just trivial. Clearly, the sign of delta 1 must be positive if I want to have some kind of limit in a possible procedure, in a possible limit procedure as delta 1 goes to 0. Right, so this operator here is a classical viscous Hamilton-Jacobi operator. So it's pretty relatively easy to handle. Now let me try to motivate this delta 2 here, right? So now, in order to motivate it, let me forget about the approximation. So forget about the delta 1. I just want to show you that adding delta 2 here doesn't change too much the situation. So let me consider this modified Eichhorn equation. Let me try to motivate it. So what do we have? What does this delta 2 mean, actually, from the modeling point of view? What I'm doing is, okay, take once again this polar decomposition of the velocity. So z is the direction. What happens? Take the modulus of v. This is what you get. Once again, you have a function which is 0 when rho is 1, and it's monotone decreasing starting from a maximum value which is 1 over delta 2 plus 1, but you can modify that by just multiplying by 1 plus delta 2, so that doesn't really matter. And okay, so this is just explained here. Let me show you this by a picture. So the picture on the left-hand side is the original model, and this is the modified model. So you only have this little, this kind of zero derivative point for the velocity here. So it basically means that when the density is very high, the velocity is a bit less than in the original model. So right, there is some kind of degeneracy in the acceleration, right? But what about the direction? Because you might say this is not the only modification that you have. You're also modifying the equation for the direction. So what is this telling me? It tells me that basically the main difference is when rho is 1, the gradient of phi is no longer infinity, if you want, in absolute value, but it's still finite. Okay, but so this is a possible drawback. On the other hand, I'm going to tell you, when rho is 1, v is 0. The speed is 0. So I don't really see that too much, right? So individuals do not move at all when rho is 1. So I don't see this modification too effective. Of course, it's a bit different. It's slightly different. And this is actually one reason why we hope to remove this kind of approximation in the future, but for the moment, this is what we have. All right, let me now come to the mathematical theory of the approximated model. Okay, for simplicity, we shall work in 1D. And so this is just the model rewritten in 1D. So this is the delta 1 and delta 2. I shall assume that they're always strictly positive all the time. Let's set the model on a bounded interval, namely, for instance, -1, 1, with homogeneous Dirichlet boundary conditions, which is actually what I expect. I mean, they really mean that I'm trying to. So you can see by some kind of modeling by simulations that in fact this will account for my domain to get empty after a while, so you don't see pedestrians anymore. Now the point is the following: setting a Dirichlet boundary condition for a conservation law is not so easy, but again, there's a huge literature covering that kind of issue. And the way to do that is this one. So this is this kind of formulation goes back to, for instance, to Bardos and other people in the early 70s, I think. It's basically telling you that I should prescribe a boundary condition only when the characteristics are incoming to the domain, right? So they are directed towards the interior of the domain. So now, just to simplify the coverage, let me call G to be the product of rho times f squared, so that I can call this function here G of rho. All right? Okay, so if you do some computations, in fact, what you realize that is just that the G should have some kind of monotonicity at the boundary. This is another way to set the boundary conditions. Okay. In particular, for those who have never seen this kind of problem, what you do in order to realize what is the exact value at the boundary, you solve a Riemann problem. So you take the 0 value on the left, say for instance if you're working on the point -1, so this is my interval -1, 1. If I'm working here, I have to solve a Riemann problem between the 0 boundary value and some kind of rho plus on the right. So solving a Riemann problem just means finding the unique entropic solution of the conservation law. And this provides some kind of result. Depending on the value of rho plus, you might have a shock or a rarefaction wave. So that depends on the value of the right-hand side. Okay, so as I said, I need to define entropy solutions, and so here is the precise definition. I'm working with a couple rho phi, so phi is part of my solution, the potential phi, right? So I'm going to call rho phi a weak entropy solution to my system if the rho component must be a boundary variation function and L infinity. Phi should be in W2 infinity. The conservation law should be satisfied in entropy sense, where I'm using the Khrushchev formulation, using basically just the Khrushchev entropy is the absolute value of rho minus k for some constant k. And here you see the boundary term appearing. And finally, the smoothed or regularized iconal equation should be satisfied almost everywhere. All right? Okay, so as usual, what do? We apply the vanishing viscosity method. So we add a little bit of viscosity in the continuity equation for a small epsilon. And so now the question is, what is the right boundary condition? And the answer is very easy. You just have to put homogeneous Dirichlet in the classical sense. And classically, it's well known that the set of boundary conditions that I prescribed before is what you obtain in the limit when you set a homogeneous Dirichlet for your model. This is true even in a non-homogeneous case. So whatever kind of Dirichlet condition in the viscous equation in the limit becomes exactly what I said before. And of course, I have an initial condition. So let me just mention that for this kind of system, you have a classical theory, which is just it's just a non-degenerate parabolic elliptic system. Everything is nice because you can prove that rho always stays between 0 and 1, if so initially, which is consistent with my model. All right. Okay, now it is not occasional that in my definition I required rho to be a boundary variation. So for those who know this topic very well, that basically means that I would like that in order to obtain a solution, I need to estimate the BV norm of the viscous approximation, right? So, but the thing is that I have some coupling, which is definitely non-trivial with the potential phi. So I need some estimates on phi as well in order to proceed. So phi is the potential. So here is another, just rewriting the equation for phi. Right? So you have this Hamilton-Jacobi term on the left-hand side, and this is the regularized right-hand side. Now, as I said, this is pretty relatively easy to handle, and one way is to introduce the very famous Hopf-Kohl transformation, which basically turns these operator into a simple Laplacian, right? And in fact, this is what you get. So if psi is exponential of minus phi divided by delta 1, that's what you get. So that's the new equation for psi. You have delta 1 square psi sub xx equals psi times the whole right-hand side here. And the boundary value is now 1 and not 0 anymore. Okay, so first lemma is that I can do some estimate on psi, namely estimate the H1 norm, and also because of that, the L infinity norm of the second derivative. How? That's very easy. Just take the equation for psi minus 1 and call it psi tilde. That's what you get. You have, of course, some kind of remainder, and the boundary value here is 0, so it's easier to deal with. You multiply your equation by psi tilde, you integrate by parts, and you get a nice estimate for the gradient squared, right? Now here I'm crucially using the fact that delta 2 is positive, right? So this right-hand side here cannot degenerate. So by a simple Young inequality here you get that psi tilde is bounded in H1 and therefore in L infinity, and therefore by plugging this into the equation I get also the estimate for the L infinity norm of psi sub xx. So psi has two bounded derivatives. Now one more thing is psi is non-degenerate, so it's never 0. This is easy actually. It's just a consequence of the fact that the phi satisfies some kind of minimum principle. You can rewrite the equation for psi in this kind of way, so you can see that this term is always non-negative, and therefore the second derivative of this function is always non-negative, so it attains the minimum at the boundary, and therefore phi is always bounded from above, and therefore psi is always bounded away from 0 because this ratio here is bounded from below. Okay. So these are just technical estimates. Why do we need them? We just need them to estimate the BV norm of the density, as I said. So I promised you to do that. So let's start. How do you usually estimate the BV norm? You just take the derivatives and estimate them, the first derivatives in L1. All right? So that's what you're going to do. So that's pretty classical. You take a smooth approximation of the absolute value as gamma goes to 0, and you estimate it in the usual way. So here is where the coupling with phi appears. Now I'm going to skip the details because this is pretty classical, but basically you can see that when you integrate by parts, you need 3 derivatives in L1 for phi in order to estimate this term, and 2 derivatives in L infinity, and therefore you can conclude basically by some simple Gromov inequality that everything goes as planned. Remember that rho is in L infinity, so that's pretty classical. I hope I was able to convince you that these kind of estimates that I proved before on phi allow you to close these kind of estimate. Now here we come to a major difficulty if, for instance, you consider the model that, the approximation that I told you before. If you remember, I said something like this: you could eventually approximate your eikonal equation in this way. Right? Now, a major problem when you use this approximation instead of the one that we're using now is exactly here. When you try to estimate the time derivative of the density, you can clearly see, and it's going to be clear from the proof, that in order to do that, you need to estimate derivatives of phi with respect to t. So in this case, that's, I mean, we were not able to do that. So how do you estimate time derivatives of psi? In this way, you can do it thanks to the Hopf-Kohl transformation. So the use of the Hopf-Kohl transformation helps a lot in this kind of framework. And so, in particular, you can see that the L infinity norm of psi, you gain something. I mean, you can estimate everything basically in terms of the L1 norm of the derivative of rho with respect to time, which is actually what you need to estimate now in order to close the BV argument. All right, so I think I can skip the proof here. This is basically very similar to the one before. You can see here that, again, I can integrate by parts and estimate the H1 norm of psi sub t squared. All right, so now in a very similar way as before, you can prove that the L1 norm of rho sub t is as well bounded. I'm always working on bounded time intervals here, of course. And again, the strategy is taking approximation of the absolute value and derivate, differentiate with respect to time and whatever. All right. So now you can do the viscosity limit. So what we have is that we can prove that, as we did, that the BV norm of rho is bounded uniformly with respect to epsilon. So we can send epsilon to 0 and get a strong limit in L1. And actually, this is enough to pass into the limit into the entropy formulation. And the estimates are much stronger, of course, for phi, because you can get an L1 estimate for L1 compactness for phi sub xx. All right, and then I have my theorem, which tells me that I have existence of entropy solution when the initial datum is W21. Okay. Now, what about uniqueness? Okay, here I have to hurry because it's actually pretty late, but about uniqueness, it is well known again to the specialists that whenever you have a conservation law with some coupling and you want to prove uniqueness in the Khrushchev stance, you need some kind of stability with respect to the coupling term, right? For instance, if you think of also models in biomathematics like chemotaxis or something, for instance, in semiconductor theory, you see that very often as well. Right, you have a transport term, you have a right-hand side. If you have some stability with respect to the right-hand side, to your inhomogeneity, then you can somewhat prove uniqueness. And this is actually a strategy which goes back. I mean, it's pretty recent. I mean, to my knowledge, the best formulation that I've seen is a paper by Carlsen and collaborators in Norway. Okay, so how do you do that? I want to show you that basically, if I take two potentials, their difference is controlled by differences of rho. That's what I'm roughly saying by these three estimates here. How you do that? You take two equations for phi with different rhos, of course, and you subtract them, and now once again you do energy estimates, right? So once again you wanna get an estimate for the absolute value. So you regularize it, you smooth it out in the limit. And at the end, you can control the difference in L1 with psi and psi bar in terms of rho and rho bar. Right? Now you can do the same also for this difference here by multiplying by the sign, by an approximation of the sign of this difference. All right. Now, as I said, this automatically gives you uniqueness, and this is due by a paper by Carlsen and Riseborough in 2003, in particular, if you want to have the exact reference that we're using. And it is based on this kind of stability. So this is just what you simply get by applying very straightforwardly Carlsen and Riseborough's technique. Now with the stability result that I had before, I can control this difference by rho minus rho bar. So for short times, that works, right? Because you can always bring this guy to the other side. And same here. This guy is controlled because it's the BV norm of rho, right? And therefore you can iterate and go on. Okay, so this is to prove existence and uniqueness of entropy solutions. So good. Now the thing is that of course we are not too happy of the fact that this is just an approximation, it's not the original model. So at least we tried to see what happens in the original model in two ways. Namely, first, we tried to do some characteristic calculus. Second, we did some numerical simulations. Okay, first of all, what about the original model in 1D? Is there any way to write it in a simpler form? And the answer is yes, because after all, this guy here is just an iconal equation with a non-constant right-hand side. If you know in advance what you want to get as the unique solution of this equation, namely the only semi-concave solution phi, what you do, you just integrate from -1 to a certain point x0, and same on the right-hand side. So in order to get rid of the absolute value, and you can basically get some kind of explicit somewhat formula for phi. And the most interesting part is that actually phi has a unique turning point. What do I mean by turning point? So phi is 0 at the boundary. It will be increasing for some time, so this is definitely not increasing, right? Then there is a one point x0, which actually depends on time, and then I have a decreasing part. So, and this picture can be as nasty as you want. I mean, it can be of course, very non-symmetric, because it depends. This kind of rearrangement depends on the density rho, right? So, and of course, if you integrate the iconal equation first from -1 to x0 and then from x0 to 1, you can get an explicit formulation for the turning point. Well, it's not really explicit, but at least it involves in a very clear way the density rho here, right? So this is a formula which defines in a unique way your turning point x0. Now, therefore, what do we know? We can say that we can now write the first equation in this way. Let me use this kind of trivial formula, and let me substitute it here, because I know that if I write phi sub x as the absolute value of phi sub x times the sine, I can use the second equation and get rid of this one of these two terms, f of rho. So here I get rho f of rho times the sine of phi sub x sub x, right? But I exactly know what this term is in terms of the turning point x0, right? So this is one way to decouple the equation. Of course, the coupling with the coupling here is very subtle, because x0 depends on rho by this formula. So if you want, the reformulation of the system is this equation here coupled with this formula here. And this is what I mean by when I say that this is it's a non-local, it's some kind of non-local conservation law. Okay, so the boundary condition can be set up in the same way as I said before, with the Bardol's strategy, by solving Riemann problems. What you see more precisely, because here we can really compute the characteristics, is that all the characteristics point outside when the trace of rho is between 0 and 1/2 of the maximum density, and they point inwards when when rho is larger than 1/2. So that basically tells you that the people try to get out when the density is not too high at the boundary, and they change their strategy when there's too much people, when the crowd is too dense at the boundary, right? Now you can clearly see that this kind of behavior is biasing the turning point, the behavior of the turning point as well. So that's why the behavior of the turning point is typically non-local, right? Okay, so this is just what I said. So they point outside when the trace is between 0 and 1/2. Therefore, I cannot impose any condition in that case because they are going outside. And otherwise, I have to solve what? I mean, in fact, when the trace of rho is between 1/2 and 1, in that case, I have a rarefaction wave, because in that case, the only entropic solution is given by rarefaction wave. So basically, what happens is that I have to connect the two states rho, trace of rho, whatever, and 0 by a rarefaction wave, and it turns out that the value of the boundary will always be 1/2. This is again pretty classical. If you take a Witham equation for traffic, you see exactly the same thing, with the difference that here the behavior is reversed at the 2 points at the boundary, right? So I really mean that for high density, you always point inwards, right? So just to say that so somehow the behavior of density does not depend on the direction, but I really have to compare the direction with the fact that I'm pointing outside the domain or inside the domain somehow. Okay, and here is the exact formula for the characteristics. You can get some kind of Rankine-Hughes condition as well, right? So to find a jump condition. In particular, some interesting point is what happens at the turning point. So do I have some kind of jump condition at the turning point as well? And the answer is yes. It's actually a pretty degenerate condition, because it's basically telling me, so we can see that, for instance, with a very simple example. Take a constant initial datum, right? Right. So since the initial datum is constant, what I expect is my solution to behave in a symmetric way so that the initial turning point will be here, right? And it actually always stays there. So the turning point, by simple symmetry argument, is not moving in this case. It's just constant. So the question is, what happens here? What is the behavior of the solution close to the turning point? You would expect at the very first stage, okay, it's just constant. I mean, it's a constant solution, so why not just keep it constant? And the answer is that this is not possible, in fact, because I have a velocity pointing in this direction and another one pointing in this direction. So what you have is a formation of a vacuum inside. Which is something, I mean, surprising mathematically, but not so much from the modeling point of view, because you have to see this turning point as a situation in which on the right hand side of the turning point, people want to go towards the boundary. On the left hand side, they want to go towards the boundary. So it's clearly you have a formation of a vacuum. So it's pretty reasonable indeed. And indeed, this is the only entropic solution in that case. You have no rarefaction at the turning point. You really have a discontinuity. All of a sudden, you have a formation of a hole. And again, you can recover that by simple Rankine-Hughes condition. So you have a formation of a vacuum at this point. Now here I have some pictures, some movies, just for a very simple reason, because I would like to show you that, in fact, when this is not the case, namely when the initial condition is not symmetric, the turning point is moving, and it can be moving very, very nastily. So let me show you that with this simulation. Okay, now it's, you see at some point, okay, here you don't see much. This is just to show you that, in fact, you have this formation of the vacuum inside. Let me play it once again. So you see that you have this vacuum. So they are both trying to reach the boundary. And here also you see that this value 1/2 is somewhat achieved for a while at the boundary. Now with the next movie, I want to show you that the behavioral turning point can be pretty nasty. In particular, it's not easy to control its time derivative. So now you will see that the turning point will change direction very. You see? it was going this direction, now it's moving on this other direction. So it may change direction, which makes it a bit more difficult, right? Because if you want to attack now this case, which is the original formulation of the model, you need to control somehow the behavior of the turning point, especially its time dependence. And now we don't know how to do that actually, and this movie shows you that this is not necessarily the case that you can do that. So it's not so easy to do that. Okay, so that was enough. Thank you for your attention.
Thank you very much, Marco. Are there any questions? I want to go back with one little question to the very beginning. Somehow you do get the feeling that the splitting of absolute value of the velocity of your conservation law towards the direction somehow is maybe very hard, right? I mean, it results in a very hard problem which you have to regularize twice, and somehow I don't wonder, I mean, if you could actually modify that in some sort of less strict way. I mean, like as you said, I mean, the velocity modulus, you just modified some little thing down there, right? And that makes things much nicer, and you wonder how much, I mean, this is anyway, it's a model of something which is human, so there should be a lot of robustness in the model anyway.
Yeah. I think you could try. I mean, I'm pretty sure that if you require the velocity to behave linearly close to this kind of maximum density, you basically get to the same point. I think as long as you let it have a zero derivative, not necessarily quadratic, as I take it. Is that probably what you mean?
Yeah.
So with this, I would just want to say that, of course, I expect there are many other ways to modify the original model, but I don't know if this is a good answer. I mean, I expect that if I take it straight, if I take just a straight line, that doesn't work, because basically this is the original system.
Maybe we discussed it.
Yeah.
Any other questions? Well, if not, let's just thank Marco.
Thank you.